joint work with Rob Kirby. We keep trying to write it up and keep being very slow, but in some sense it keeps changing as every time we try to write it up it changes a little bit. So I don't know when. I should really say it's still work in progress, but my idea is to try to get, since often when I give talks I have a problem of going on and on and on, and then I don't say any theorems till the end. So I'm going to try to do the opposite and go relatively quickly to some statements, and then I'll try to explain and motivate and maybe give you some idea of the the ideas of the proofs. So if you have a question, why is he doing this, just wait with the question. Okay, for a little bit. Right. But I need to give some definitions, of course. But the rough idea, at least, is Morse theory studies generic maps from manifolds to one-dimensional spaces, usually R, sometimes the interval, sometimes the circle. And why not study generic maps to two dimensions? Singularity theorists have thought about this in some sense, but I don't think they really thought about it in the sense of what does it tell you about the topology of manifolds, right? And there's also the idea of Morse theory gives you handle decompositions. What do generic maps to two dimensions tell you in sort of in an analog with handle decompositions? But anyway, let me just start with some basics about smooth maps. And so first of all, if I have a smooth map F from one manifold M to another manifold N, I'll say that it's stable if for any perturbation f sub t and n, so this means t is just some parameter, maybe just from minus epsilon to epsilon, and it's the map is varying smoothly with respect to t. There exists some epsilon greater than 0, such that for all t between minus epsilon and epsilon, let's see how do I want to say this. Yeah, there exists. So what I want to say, the idea is that as long as t is between minus epsilon and epsilon, f sub t looks just like f, up to reparametrizing in domain and range. Okay, so there exists some phi from m to m diffeomorphism, and some diffeomorphism psi from n to n, and then such that f equals psi inverse composed with phi, composed with f sub t composed with phi. Okay? The idea is you do a small perturbation, and up to changing coordinates in domain and range, it looks like you didn't do anything. Okay? So that's this notion of stability. And let's see, if the dimension of n is 1, then stable maps are Morse functions. Okay, so this notion of stability is sort of the reasonable thing to, if you want to generalize the notion of a Morse function. Also, and they are generic. There's some funny thing about when the dimension of n is maybe 5 or 6 or something, I don't know about. Suddenly, stable is not generic, which is weird, because you might think it's almost obvious. Stable is obviously an open condition, but it's not actually obvious that stable maps are dense. But that's a weird high-dimensional issue. And when it's 2, it's also generic. And then locally stable maps, we know what Morse theory is. So locally, when dimension n is 1, the maps look like you sort of have two models. One model for is that x1, you sort of have coordinates x1 up to xn, maps to just x1. This is if there's no, it's a regular point, a neighborhood of a regular point. You can always find coordinates in domain and range if the dimension of the target space is 1. I'll talk about dimension 2 shortly, right? Or you have sort of a local model, what I'll call 2 sub k. It depends upon a number k, which is the index, which is x1 up to xn maps to minus x1 squared minus dot 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 minus xk squared plus xk plus 1 squared plus dot 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 plus xn squared. Okay, so the standard Morse critical point. So this is lots of ways to prove this, but you can think of this as a result in singularity theory. It fits nicely into sort of the René Thom catastrophe theory program and so on. Okay, so I'll talk about cases when dimension of n is 2 shortly, but first let me talk about suppose now I have a homotopy f sub t from m to n. And I want to talk about a certain kind of stability for that homotopy. Okay, so I'll say that this homotopy is stable if, well now, in other words, I'm not talking about the map being stable for a fixed time. I'm talking about as a homotopy, what does it mean for the homotopy to be stable? So I have to talk about a perturbation of that homotopy. Okay, so if for any, let me see, for any f sub s and t, so now I think of f sub t as the fundamental object. Sorry, what did I not write down here that you probably knew I was saying? f0 equals f. Okay, in that case, in other words, I was talking about a perturbation of f, right? So similarly, I want to talk about a perturbation of this homotopy. So f0t is equal to ft. Right? Then again, I'm just going to say there exists an epsilon, and then for all s between minus epsilon and epsilon, there exists some, the reason there's some things you might not think of in terms of what's the right way to say stability here. So what I should say is there exists a change of coordinates in domain that is allowed to depend upon t, and a change of coordinates in the range that is allowed to depend upon t. And we should also allow ourselves to change the t coordinate. So these are both diffeomorphisms that depend upon t. And then I want some diffeomorphism from R to R, or whatever the domain of the variable, sorry, let's call it the sigma. No, tau, that's right. R to R or minus epsilon, whatever the domain of this parameter t is, such that, so I want to express a relationship between f sub t and f sub s t. And the first thing is I'm going to allow myself to change the time coordinate by a slight reparameterization, and then I'm going to allow myself to pre and post compose with these changes of coordinates. Okay.
So if you use the domain of tau is finite interval, you want that interval to be preserved?
Yeah, exactly. Right. Yeah, R or the interval. Yeah, actually, usually it's 0 to 1, right? And all of these stability notions, there's local versions of them as well, which you can express formally in terms of germs. You could talk about germs of maps, germs of deformations, and stable germs of deformations. And when I say these are the following local models, what I really mean is this is a complete list of germs, stable germs, up to this kind of equivalence. Okay, and that's how it's stated in the literature on this subject. And okay, so this is yes?
Is this the same as saying the map from M cross the interval to N is stable?
No, thank you. That's exactly the right point. That's not the same. So you could think, what about the map F, capital F, right? The usual thing you do at home, capital F from interval across M to N, or even from you might say interval across M to interval across N. The various ways in which you can promote this properly to a map from the interval across something, right? And it's not the same as saying that that is stable. And this is the point. The point is that this reparameterization of the time variable is not allowed to know anything about the space variables. Okay, if you just said, let's take f from I cross m to n, and let's ask that to be stable, right? Then you would just allow yourself to precompose with some diffeomorphism of I cross m, which can freely mix up the I and the m coordinates. this says that the I coordinate, the way you reparameterize it, is not allowed to be influenced by where you are in M. But the way you reparameterize M is allowed to be influenced by where you are in T. Does that make sense? Sort of, yeah. And that's an important point. And sometimes this notion of stability is sometimes called one-stable, to emphasize that, right? Okay, so if dimension of n is 1, then this is the natural notion of sort of, well, I'll call it a deformation of Morse functions. But it's when you learn Morse theory and learn two Morse functions are connected by a sequence of functions, and then there's some isolated times at which it fails to be Morse, and during those times you have births and deaths of canceling pairs of handles, and so on. This is exactly the kind of generic deformation that gets you from one Morse function to another. So, and it's generic. And the study of such maps, I guess, goes on to the subject of the title of surf theory. I always used to think it was, I heard Rob Kirby talk about surf theory, and I always thought it was SURF. And I irritate my Francophone friends tremendously by calling it surf theory, but it's surf or something like that. But, okay, so. We'll come back to that, but local models for such things are. Oh, and then, well, when I write down the local model, you'll see, but a fact is that a stable homotopy will be Morse for all but finitely many times. Okay, and the local models are. Maybe I should squeeze it out. Yeah. Well, the local models are those models, 1, 2 sub k, and then one more model, which is called 3 sub k. And it looks like this, minus x1 squared. I'll just write down what the right-hand side of the function is. So it's minus x1 squared minus dot 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 minus x k minus 1, xk squared. And then we have a cubic, xk plus 1 cubed minus t xk plus 1. And then we have plus xk plus 2 squared up to xn squared. And if you've ever thought about this, this is exactly what happens when you have a birth. As t, there's a t parameter. These two models don't involve t. So it's saying sometimes, of course, nothing is happening. Interesting in your deformation. And then, but this is the local model that involves t. And precisely when t is less than 0, you have no critical points. And then when t is greater than 0, you have 2 critical points of successive indices. The indices will be k and k plus 1.
So this is k plus 2?
Oh, sorry, k plus 2, thank you. Okay. And then I'm only going to continue this line of thought one level further, but it's going to be important. Okay, so let me not, rather than write everything down so carefully, one can also think about a homotopy of homotopies. And the reason I'm going to want to do that is because I'm going to later want to think about homotopies of maps between homotopies of maps to 2 dimensions, and they'll sort of locally interpret that as related to homotopies of maps to 1 dimension. Okay, so there's a notion of stability, and it's all the same, blah, 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 blah. I just have to tell, well, I need a third parameter, so I have sort of f sub r, s, and t. And r is the parameter I need to say for all epsilon. There exists an epsilon, so that for all r between minus epsilon and epsilon, etc. But let me just tell you how this changes. Okay, so this is going to have f sub 0 st equal to the given fst. And the way that this changes is f sub st will be equal to some, well, I'll reparameterize the range in a way that is allowed to depend upon S and T. And then I'll have F sub R. And now I'm allowed to change the S coordinate in a way that depends upon S, and I'm allowed to change the time coordinate in a way that depends upon S and, tau sub S of T. And then phi sub ST. So this is sometimes called 1-1 stable. The idea here is that there's a hierarchy of these parameters, okay? And so I can't re-parameterize S. When I re-parameterize S, I'm not allowed to know about T. When I re-parameterize T, I'm allowed to know about S, but I'm not allowed to know about where I am in the manifold. When I re-parameterize the manifold, I'm allowed to know about everything. Okay? So this is somehow the natural equivalence relation on such maps, which gives us this notion of stability. And I'll call, so again, when dimension of n is 1, these are stable as generic, and I'll call such a thing a deformation of Morse functions. Let me not write down I will write down local models for this eventually, but I want to move on to talking about maps to 2 dimensions shortly. Okay, so it's generic, and there exist local models. And the local models are, and again, these are just come from analyzing stable germs of such maps under the appropriate stability. And if you want to understand how could you possibly produce all, you can keep going, right? How do you produce local models? Well, there's a paper by Wasserman. Let's see. I learned about this mainly by reading a paper by Janke Lekili, who was writing, and I'll tell you more about what he was doing as a motivation. But so it's a paper on wrinkled fibrations, I think he calls it. Anyway, but in that he references this paper by Wasserman, which sort of gives an algorithm for producing local, for producing lists of all local models for stable maps of whatever kind of stability you might consider, right? So in some sense, there's an algorithm, and there'll always be a finite number of local models you can have. Okay. Anyway, let's now start talking about maps to dimension 2. Okay. So stable. So maybe give a definition. A stable map F from M to N with dimension of N equal to 2. Let's see, I will say is a is what I'm going to call a 2 Morse function. Okay, I mean, why it's kind of like we have 2 categories, and cobordisms between cobordisms might be called 2 cobordisms. I don't know, maybe it's not a good idea, but anyway, there's some idea, it's all right. So let me just say one thing is that if the boundary, everything I'm ever going to talk about, unless it's called R or Rn, is compact. Okay, and in particular, if the boundary of M is not empty, we should require that F restricted to the boundary of N maps the boundary of M to the boundary of N, and that should be Morse. Okay, the natural boundary condition. Okay. Okay, so one fact is that stable maps to 2 dimensions look locally like what Ko was talking about, which is look locally like maps of the form T, comma, x1 up to xn maps to T, comma, and then f sub T of maybe I'll just write this way, t comma p. Sorry. T comma ft of p, where f sub t is a stable homotopy of maps from dimension n minus 1 to from dimension n minus 1 to dimension 1. Okay, now you might think this contradicts what I said to Coco, that this is different, but notice that here we have the extra time parameter in both domain and range. Okay, so in some sense, well, what I'm saying is that if you have a stable map to dimension 2, then you can find coordinates in domain and range. You can sort of split off a time factor from domain and split off a time factor from the range locally, and then you can sort of show that you can reparameterize things so that it's constant. It means the identity map in the time factor, and then in the other factor it's some deformation, some homotopy of maps from this space or space coordinate in the domain to this one real coordinate in the range, and that'll be stable. So once I start talking, once we start analyzing what these things look like more carefully, that'll be the key to getting some intuition. And that's also why I wanted to talk about the case of maps to dimension 2. And the other thing then is stable homotopies. I think the f sub s from m to n with dimension of n equal to 2 look locally like just t p goes to t comma f sub st of p, again for f sub st stable. So what you may or may not have some intuition about what these things and these things look like, but what you should get from this is that if you want to study maps to 2 dimensions, they locally look like something, time cross something, except that globally you don't know what direction is time. Okay, but locally it sort of just looks just like something you might understand from Morse theory, except that globally, the direction that you call time will keep changing. And so I'll draw some pictures that hopefully will make that a little clearer. Let me now add an adjective to a lot of these settings. Okay, in Morse theory, in various contexts, it can be useful to look at Morse functions that do not have minima or maxima, or have as few minima or maxa as possible. Okay, for example, if M was a cobordism it was a connected cobordism from a non-empty manifold to a non-empty manifold, you would naturally be interested in Morse functions to the interval which had no index 0 or n critical points, where n is the dimension of M. Okay, or you might be interested in maps to the circle. If n had non-trivial pi 1, you could be interested in maps to the circle representing a certain homotopy class which have no critical points of index 0 or n. Okay, and so and this comes up in various contexts. And then one also could be interested in, suppose you have 2 such Morse functions with no minima or maxima, can you find a homotopy from one to the other that does not introduce in the middle minima or maxima, index 0 or index n critical points along the way. In fact, the fact that if you start with and end without minima or maxima, that along the way you don't need to introduce any minima or maxima, is sort of critical to Kirby's proof of the Kirby calculus, for example. So in the interest of sort of replicating those, the main theorems I want to talk about are sort of analogs of those results in the case of mapping to 2 dimensions. Okay, so let's say that a Morse function is, let's say that this is indefinite if you never have k equal to 0 or or n. Okay? K equal to 0 or k equal to n is exactly what gives you local minima or maxima in a Morse function. Okay? So we never have index 0 or index n critical points, and that's what I will mean by an indefinite Morse function. Okay? Why does that? Because when k is 0, you have a definite form here, and when k is n, you have a definite form here. Similarly, I will say that a deformation of Morse functions is indefinite if you never, let's see, what do we want to say here? Maybe I'm not using the board so well. What? Yeah. So a deformation of Morse functions is indefinite if you never have, well, let's see, the smallest k can be is 0. That could still happen. The largest k could be, since you have to go up to k plus 1, is n minus 1 in this case. Okay. And then, what will happen if you have k equals n minus 1, you'll have a birth of a pair where one of the critical points is just sub-maximal and then the other critical point is maximal. Right? And then you can do exactly the same thing for these two Morse functions. You could say the two Morse functions are indefinite if these local, if the f sub t's are indefinite. Okay? And so it just means that whenever you sort of think of this local picture, this f sub t never has minima or maxima. Okay? And that's the analog. This is the setting in which I want to talk about. I said I would delay motivation till later, but let me just say one thing for those who've heard something about it. If you've heard people talk about broken fibrations, broken Lefschetz fibrations, and so on, that's the case of maps from dimension 4 to a 2-sphere, where and then this, which are indefinite. So two Morse functions to a 2-sphere, which are indefinite. That's what some people, Janke Lekli and Tim Perutz and others, are calling broken fibrations. So that's kind of the setting for it. But okay, let me try to state some theorems now. So any questions on the definitions? Yeah.
So generic is in what topology?
Oh, I was really hoping you wouldn't ask that. Generic for me means they exist. Okay. So generic means I can find them, right? Generic means there's a paper somewhere that tells me that's generic enough that I can find their existence. So to be honest, that's not. I'm not qualified to say much more than that. Okay, so I can probably find the appropriate references that will tell you, but and I should really know the answer to that. I don't. Okay, I probably will know the answer 10 minutes after this talk, but right now I'm confused by it. Yeah. Okay. I mean that's exactly the right question, but the only use I make of generic is, if I want them, I can find them. Okay. And well, in particular, if you have a smooth function, probably it must be C infinity topology, because if you have a smooth function, I want to know close by to it. There's a function that satisfies that property, right?
So your map after general is it smooth or continuous?
All maps are smooth. Yes. Sorry, I should have said that also. I forgot there were people in the audience who think about C0 stuff. Okay. All right. So here's a theorem. So for every connected compact smooth X, and I need dimension of X at least 3, And let's suppose that here I want the boundary of x to be non-empty. And I want to be given an indefinite Morse function g from x to the circle. Okay, so of course such a thing might not exist, even if the boundary is non-empty, because for algebraic topology reasons. But anyway, suppose you have that. So indefinite means no index 0 or index n-1 critical points now. Sorry, g from boundary x. Okay. There exists an indefinite 2 Morse function, capital G from x to the disk, with capital G restricted to the boundary of x equal to little g. That's part 1, and then that's part 2 says that given g and g prime from x to the disk, which are both indefinite 2 Morse functions, suppose that g restricted to the boundary of x is equal to g prime restricted to the boundary of x, then there exists a deformation, which means a stable homotopy, g sub s from x to the disk, with g0 equal to g. Sorry, an indefinite deformation. This is the indefinite. g0 equal to g, g1 equal to g prime, and of course I want it to stay fixed on the boundary for all time, so gs restricted to the boundary of x. So let's absorb the statement here. Okay. Given a connected compact x with dimension x greater than or equal to 3, I guess I should put the 1 down here, because those hypotheses apply to both cases. Actually, this hypothesis here is where 1 starts. I need the boundary to be non-empty for both cases. And given an indefinite Morse function from the boundary to the circle, I can extend that to an indefinite 2 Morse function from g over the disk. And so it's if I erase the words indefinite, this is just genericity. Okay, I can construct random smooth maps satisfying the property, then I perturb them, and they're generic, so they're stable, and I'm done. Okay, so it's an issue of getting rid of the definite critical points. Okay, and then now this says if I start with 2, which are indefinite 2 Morse functions, so they don't have minima or maxima locally, and they agree on the boundary, then I can find a deformation which also remains indefinite, so it never introduces minima or maxima, going from one to the other, remaining fixed on the boundary. So again, if I didn't ask for this word indefinite, it's just genericity, and then the point is to choose some generic one which is stable, and then try to get rid of the definite stuff that arises. Okay. And so far as we know, this is a new theorem. A corollary of this is not a new theorem, but I sort of like the fact that what I'm going to say now follows from the case of the disk. And so, which is that given a closed connected x, dimension x bigger than or equal to 3, and given any homotopy class of maps from x to S2, there exists in, let's see, one is, there exists an indefinite Morse function, two Morse function, capital G, from X to S2 in this homotopy class. Let's see, certainly, I forget the history. At the very least, when dimension of X is 4, this is a result of Saeki, who views it in the context of singularity theory. I should know this. I can't quite remember whether Saeki did it in other dimensions, but it probably follows easily from that, what he did in other dimensions. And then given two G and G prime, which are indefinite, two Morse functions from X to S2, which are in the same homotopy class. Of course, you need them to be homotopic. There's obstructions otherwise. Let's see, there exists an indefinite deformation I'll just say GS from G0 to G1. And so this just means that you can get from one to the other without introducing any definite critical points. And this is in dimension 4 equal to 4. This is a result of Jonathan Williams. Jonathan Williams' proof, and a proof that Rob Kirby and I had sort of around the same time, very much uses the fact that you're mapping to S2, and it's sort of somehow for us was unsatisfactory because sort of, you know, why should it depend so much upon the base being S2? We really sort of felt that the result should also be true for a disk. So the point is, I won't talk about the proofs of these at all, but it sort of pleases me that the proofs for S2 should follow from the proof for the disk. And also Saeki's argument also really uses the fact that you're mapping to the two-sphere. And so neither of their arguments really obviously work for the disk, which is interesting. And you can say things about maps to other surfaces that are more complicated. Saeki also spells out obstructions to the existence of indefinite two Morse functions mapping to other surfaces, which have to do with homotopy classes. And so, modulo those obstructions, I sort of think we can probably, give general results for other surfaces as well. Okay, so those are the theorems. So at least I got so far as to state our theorems. And then the point is, I wanted you to think that this is sort of the analog of the statement that if you have a compact connected cobordism between two non-empty manifolds, there exists a Morse function mapping to the interval, which has no, which sends one, the bottom of the cobordism to 0, the top to 1, and has no minima or maxima, and you can connect such by such homotopies, and then this is sort of the analog of the similar statement for the circle, right? Okay, so let me talk about motivation now, and then try to tell you something about the proofs. Let's see, I forgot completely to think about time. Will you lend me a timepiece? That'd be great. Yeah, perfect. Thank you. And so I started at 11, so I'm going to 12. Okay. Okay, so all right, so, Andras asked, why do you hate these definite stuff so much? And, if you look at Andras's talk, well, he had all these points to deal with, and all those points correspond to 0 handles and 3 handles in a Morse function on a 3-manifold. And, well, I mean, he did get some mileage out of having lots of points, but it also caused some confusion. But the real motivation for this comes from a little bit of history about, so first there's an idea that using indefinite 2 Morse functions on 4 manifolds mapping to the 2-sphere, we may be able to, there's some program in place to try to get smooth 4-manifold invariance by analyzing those things. Okay, to prove that those proposed invariants are really invariants, you would like to know how such maps vary, as you know, in a homotopy, and you would like to have some sort of combinatorial moves. And because deformations of 2 Morse functions have fixed local models, we get some sort of, if we can understand how an indefinite 2 Morse function sort of is described combinatorially, we can also understand how that combinatorial description changes in an analogy with the way in which handle-body decompositions change over time in a homotopy. But anyway, to go way back, we have Aru, Donaldson, and Kotsarkov. Well, I won't write it down, but even to go further back, you have Donaldson telling us that symplectic 4 manifolds have Lefschetz pencil structures. Lefschetz pencils are, once you blow them up, Lefschetz vibrations, and Lefschetz vibrations are special maps to the 2-sphere, from 4 manifolds to the 2-sphere. Okay, they are not quite 2 Morse functions because the Lefschetz singularities are not stable as maps from real maps from 4 dimensions to 2 dimensions. They are stable as complex maps, so they're like the complex stable local models, but when you think about them in the real world, they're not stable. Okay, and then we have I guess Donaldson and Smith, right, proposing the way to count sections or multi-sections of these Lefschetz pencils to give, and then proposing that that is related to Gromov-Witten invariance, and by Taubes related to Seiberg-Witten invariance, and we have Michael Escher proving that that's true, and then we have Aru, Donaldson, but the problem is that only works for symplectic 4 manifolds, and so for symplectic 4 manifolds are not that common, and in particular Lefschetz vibrations are not really that common, and so you have Aru, Donaldson, and Kotsarkov proving that in a much larger category of 4 manifolds, just those with B2 plus positive, you have something called broken Lefschetz vibrations, where you have Lefschetz singularities, and then you have some other kinds of singularities, which turn out to be exactly the kinds of singularities that arise in indefinite 2 Morse functions. So they introduced, well, they call them singular Lefschetz vibrations, but they've come to be called broken Lefschetz vibrations. And so the idea is you have circles of singularities, and you have isolated point singularities. And then, but they're still maps to the 2-sphere. And then Perutz spelled out a program to count multi-sections, singular or broken, in broken Lefschetz vibrations, as a way to try to get invariance. I guess I should also say in this whole program there's Taubes' idea that when you have certain generalizations of symplectic forms called near symplectic forms, you might be able to count holomorphic curves in that setting and recover Seiberg-Witten invariance, or maybe more. And so this counting of multi-sections in broken Lefschetz vibrations, these are somehow sections, but there are many levels. I'm just giving you the very impressionistic picture of this whole story. And those should somehow correspond to, in the same way that the multi-sections and Lefschetz vibrations corresponded to Gromov-Witten invariance, these should somehow correspond to Gromov-Witten invariance in that near symplectic setting. But you know, he was able to show that somehow the Floor homology was set up nicely for this program and so on, but to prove that these are actually smooth invariants, he didn't have anywhere to go until Lekili said, well, why don't you just put this in the setting of generic maps to S2 and think about deformations of them. And he sort of said, well, if you could prove, so Lekili basically asked, put broken Lefschetz vibrations in this setting of just sort of indefinite 2 Morse functions, and then ask whether you can connect any two such maps, which are homotopic, by a deformation that avoids this definiteness. And the point is, as soon as you look, if you try to enlarge this world, broken Lefschetz vibrations, or just broken vibrations, to include definite singularities, suddenly this whole program falls apart, right? You suddenly, just things behave very badly. So Leckley said, basically he asked the question, can you get between homotopic broken Lefschetz vibrations sort of with moves, which would, he described what the move should be, and he showed that it would boil down to answering the question of whether you could connect them with indefinite deformations that avoid, could you connect it with a deformation that avoids definite singularities along the way. So he described what the moves would be that would follow from this theorem, okay? But he just sort of didn't have this theorem, and it was only in dimension 4, and okay, so in some sense it's motivated by that. There's one other thing that I would like to say that is special about our results before I very briefly sketch how you prove these, which is that we can add a word to our deformations, there and there, and we can add the word special, which is like the word nice, okay? And I will try to give you some clear idea of, some idea of what it means, but in particular, what it does, and it's not in Williams's result. And when we were thinking about this carefully and talking this over with Denis Roux and Janke Leckley and so on, it became clear that there's one kind of move that could arise, even if you have indefinite deformations. There's one kind of move that could happen, which could, in principle, disconnect your let's say, if you're looking for a map from 4 dimensions to 2 dimensions, your fibers are surfaces, okay? And it's very nice if your fibers could stay connected for all time. Okay, and if you think about it, that's one reason why definite singularities are bad, because definite singularities sort of create isolated lots of zero handles create lots of isolated components, and so it can create disconnected fibers. And so definite folds are bad because they can create disconnected fibers, but there's actually another way in which disconnected fibers can arise, and I'll try to tell you quickly what that is. And we were able to show that that particular other thing doesn't happen. Okay, so it's special, which implies you never create disconnected fibers, at least in the case where a dimension of x is 4 or bigger. And there was if you're familiar with sort of thinking about holomorphic stuff in dimension 4, the really bad case is when you create isolated 2-sphere components of fibers which have square 0. And then there's this technicality comes up in Perutz's program where suddenly you've got something of dimension -1 that you're trying to count, and so. But let's now try to give you a rough idea of how the proof of just this works. Okay, and to do that, I want to say something about what those local models look like. Basically, the proofs all are guided by drawing pictures that look like this. So if I have so this is now f sub t is a map from some. So x is dimension n. Okay, but I want to think about maps from dimension n-1 to just say in R, or the interval. Okay. Because remember, locally, these these 2 Morse functions look like maps. So you'll get, let's call this little g. Well, I don't want to confuse it with that f. Okay. locally your G is going to look like a map from I cross M to I cross I of the form T, P maps to T, comma, F sub T of P. Okay, so locally we end up thinking about deformations of Morse functions, stable deformations of Morse functions, and what is very useful to draw is what's called the surf graphic for such a thing. Okay. And the surf graphic is just simply the set of points T, comma, F sub T of P, where P is a critical point for F sub T. Okay, and it's actually in this thing it's exactly the same as just simply the image of the critical set of this function. Okay, the set of critical points for this smooth function is precisely the set of points. The image of it is precisely this point. Okay, and this is something that my collaborator Rob Kirby has thought lots about. And so what does surf graphics look like? Okay, they look like this. You have, I'll just sort of draw a picture and then tell you what some of these features look like. Maybe you have a map. So I'm sort of, this is a subset of the square. Okay, these are going to be one-dimensional. And they typically just, you see a bunch of curves moving across, so graphs of functions, but then at some point you see cusps, and you may see right cusps or left cusps. And these cusps are precisely the local model with the x cubed that I was talking about before. Okay, and that's a birth or a death of a canceling pair. And you also might want to remember what the indices of these. So a point here would be this is T, and this is sort of F sub T, right? So at a fixed T value, you have a certain Morse function, and then as you cross here, maybe this is index 1 critical point, maybe this is index 2, and so forth. So that's if we're mapping to. If we're in a region where we have a local model that just looks like T, P maps to T, F sub T of P, we can understand completely this deformation of Morse functions by sort of this 2 Morse function as given by this deformation of Morse function. So there's a well-established theory for thinking about these surf graphics. Now, so we actually proved. Let me talk about how to prove. Let me give you an idea for the uniqueness part of it. I think of this as existence and this is uniqueness. People were complaining on the bus that it was misleading to call this a uniqueness statement because these things are definitely not unique. But they're unique up to these things, right? And that's the sense in which it gives an equivalence relation on these objects. But so, all right, so it's nice to think about the case where suppose X is actually what I think of, I don't know what the proper term is, I think of as a cobordism with sides, maybe you want to call it a 2 cobordism or something, a cobordism with sides from M0 to M1, and the point is M0 and M1 are both cobordisms from cobordisms themselves. Okay, so the point is, you already sort of think of this. The picture of such a thing is precisely a square in some sense. Here's a picture of X. Right, on the left I have M0, on the right I have M1. Okay, and then I have these are the sides of the cobordism. Okay, so M0 itself will be a cobordism from this to this, and M1 will be a cobordism from here to here. And we imagine that these are topologically trivial sides. Okay, so what I want to do is we actually prove a version of this theorem that's in this setting where we're mapping to the square instead. And so we want to consider maps G from X to the square. And then that makes it, we're sort of arbitrarily trying to force this as much as possible to look like we have a time coordinate. Okay? So what happens when you look at the image of the singular set for such a map? You'll see so what you want to do is you want to look at maps like this that have no singular points on the top and the bottom, and have all your sort of singular stuff exiting the left or the right, entering on the left and exiting on the right. So you have some Morse function on M0, some Morse function on M1. Then you have some stuff that looks like surf graphics. But then what can happen is basically it would be perfectly happy surf graphic just like that if there were never any vertical tangencies of the singular set. So you can think about the image of the singular set and argue that if there are no vertical tangencies, in fact, you've got a map from x to the square, and then you could further project to the interval. You could argue that if there were no vertical tangencies, in fact, the map to the interval would have no critical points, and so this would actually be a product. And then you could reparameterize so it would be exactly like this. Okay? So here's the strategy. We take two such things, G and G prime, and we try to clean up their pictures as much as possible. And this is sort of where it becomes kind of topological, Kirby calculus-like. We need to argue that think about what's happening near these vertical tangencies and pull them all as far to the left or as far to the right as possible. Same thing with the cusps. Okay, this is just very brief idea of so we call it combing. So we comb both G and G prime, and what that does is it sort of fixes them up so they both have very nice sort of behavior on the left and the right. Maybe like we can get the cusps nicely stacked together, and then we get the vertical tangencies nicely stacked in some way, and we comb them so they look very standard on the left and the right, and there's a middle third in which we just have a surf graphic. Okay, so there's a middle third in which there's a single fixed 3-manifold with a changing Morse function on it. And then we have sort of the interesting topology of X is sort of located in the left third and the right third. Okay, and then we do some extra stuff to sort of make these left thirds and right thirds identical. And that's all like we do that by thinking about the projection to the horizontal axis, which is a Morse function, and thinking about that Morse function and doing handle slides and so on to clean up the left and right thirds. And then we reduce these, we can reduce both existence and uniqueness questions to the case of actual deformations of Morse functions. And then in the sort of existence case, Rob Kirby already proved that you showed how to eliminate zero handles in one-parameter families of Morse functions, and we had to now show how to eliminate zero handles in one-parameter families of one-parameter families of Morse functions, which is another story that I clearly don't have time to tell you. So I should stop now, but I hope you got some picture of the ideas. Yeah.